Okay guys, so these are the Taylor approximations that we're going to have to start doing. This is basically the only part, the AP exam this year in 2020 that they're asking us for when it comes to Taylor series, which is good because they're not that bad, okay? So Taylor polynomials can be used to approximate other elementary functions such as sine of x, y equals e to the x, and y equals ln of x. And what we mean by that is long before there were any calculators, if we wanted to find out what sine of 0.2 is, it was a little bit overwhelming, okay? So what they did is this was created in order to approximate to almost a 0% error these functions. So what we're going to be doing is we're going to be finding the equation of the tangent line for f of x equals sine of x at x equals 0, and then use it to approximate sine of 0.2. And then we're going to answer, is this an over or an under approximation of sine of 0.2. Okay, this is going to be our first example. Or, I'm sorry, this is basically what they're asking us for. So we are going to, initially what we're doing is the function at the point is going to be sine of 0, right, at x equals 0. We know that it equals 0. That's our point. So then our point is going to be 0, 0 for the function sine of x at x equals 0. So if we know that f prime of x is equal to cosine of x, then we know that the first derivative at 0, right? So the first derivative of this function at 0 is cosine of 0, which ends up being 1. So if we have the slope, right, and we have a point, then we know that the tangent line at 0 is y minus 0 equals the slope, which is 1, times x minus 0. Here's the point. So we end up with y equals x. So knowing this, we can approximate sine of 0.2 using this derivative by saying, all right, if sine of 0.2, and we know that the approximation at 0, the slope, is y equals x, so we can say that y equals 0.2, which means y should be 0.2. So sine of 0.2 should approximately be 0.2. Because if sine of 0 is 0, right? So sine of 0 is 0, but the tangent line right here is about 1. So we can kind of say that approximately at this point at 0.2, it is basically the same thing as being on that tangent line, okay? So this is the whole idea. It's knowing that the tangent line at 0 is y equals x, and it looks like 0.2 is on that tangent line, so we're going to assume or approximate that it is. So we can use the tangent line to approximate what the value of sine of 0.2 is. Now, this is obviously an overestimate since sine of x is concave down, right? So because sine of x is concave down at 0, at x equals 0 and x equals 0.2, so we can assume that the tangent line is above. So if it's concave down, we know that the tangent line is above that function. Oops. Okay, so I hope this kind of helps, but of course it's not going to be this easy because we're going to have to get a perfect approximation. So the equation of the tangent line used in example 1 is called the first degree polynomial. So if they just wanted us to approximate using the first degree, then that means using the first derivative. Approximate using the first derivative. Taylor polynomials of higher degrees can be used to obtain increasingly better approximations of non-polynomial functions with a certain radius from the center of approximation, x equals c. This is going to be very important. So here it was at x equals 0, so our c was 0. And we will learn that if it's centered at 0, it's called something else. So definition of the nth degree Taylor polynomial. If f has an n derivative at x equals c, n derivative, then the polynomial can be rewritten, can be approximated as the function at that c plus the first derivative of the function at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared. And on and on. So the third derivative would be over 3 factorial minus x times x minus c cubed, and on until we get to this nth term. So our nth term is going to be f of whatever n derivative of c over n factorial times x minus c to the n. And this is called the nth term Taylor polynomial for f centered at c. So note, a first degree polynomial is a tangent line to f at that point c. So that's what we did here. And another note, that the nth term is the coefficient of x minus c to the n term, because this right here is essentially just going to be a number. Okay, once you actually find the derivative, plug in c over a number, it is a number. Now there's this thing called a Maclaurin polynomial. It is actually under the umbrella of Taylor polynomial. So it is a Taylor polynomial, but it's centered at 0. That means c equals 0. So sometimes they're going to tell you find the Maclaurin polynomial without giving you the center, but knowing that word right there, we know that c equals 0. Okay, so if they don't say find the Taylor polynomial at c equals 0, you know that Maclaurin means c equals 0. And in this case, if the Taylor polynomial is centered at 0, it makes it a little bit easy. So what do you notice? If c is 0, so it's still the first function, the function at c, the first derivative at c, but here's the main difference. Because what is x minus 0? Just x. X minus 0, just x, right? So the only difference between this and this is that we don't have to put the c in the term after the coefficient, okay, in the x minus c term. We don't have to put x minus 0 every single time. And then this guy right here is going to be our nth degree Maclaurin polynomial for f. It seems like a lot, but you will have to memorize. I would suggest memorizing definitely the Taylor polynomial equation. And then, of course, Maclaurin is the easy one. If you plugged in 0 here, it's just going to be x. If you plugged in 0 here, it's just going to be x squared. If you plugged in 0 here, it's just going to be x to the n. All right? So let's get into this. So let's find the Maclaurin polynomial So right away they told us this was a Maclaurin polynomial, so I know that c equals 0. It's centered at 0. Of the degree n equals 7. So what this means is that we are going to be going to the 7th derivative. Okay? Go to 7th derivative for f of x sine of x. Then we're going to use that approximation to approximate the value of sine of 0.1. So here we use the first degree polynomial and we approximated, but it was an overestimate. Here we're going to keep going to the 7th degree and then we're going to approximate sine of 0.1 using correct notation, and then we want to find the error for our approximation. All right, the first thing I'm going to do on the side is I'm going to write down all my degrees for my function. So f of x is sine of x. F prime of x is cosine of x. F double prime of x is going to be negative sine of x. F triple prime of x is going to be negative cosine of x. F to the 4th of x is sine of x. F to the 5th of x is cosine of x. F to the 6th, negative sine of x. And then f to the 7th, which is where we are going to stop for this specific equation, negative cosine of x. So here, our center is 0. So what that means is basically our x, or our c here, is going to be 0. Our x equals c, which is 0. So question is, what is f of 0? I'm hoping you guys aren't hearing all of my background because my parents are here and they can be a little loud when they're on the phone. All right, so sine of 0, of course, is 0. And then at x equals 0 here, so f prime of 0 is going to be 1. This guy is going to be 0. This guy is going to be negative 1, 0, 1, 0, negative 1. So we have all of our coefficients for this part of the Maclaurin series, of the Taylor series or Maclaurin series, right? They're all the same. So we have all of these parts. So basically we take this information and we start filling in our Maclaurin series. So Maclaurin series means take the original function at c, which was whatever c was, and c here was 0, and that was 0, plus take the first derivative, which is 1, times x. Because this is Maclaurin, I don't need to put x minus 0, right? But if you want to memorize the Taylor, you can put x minus 0 and clean it up next. Okay? All right, plus the next part is going to be the second derivative, which is 0, over 2 factorial, okay, times x squared, plus the third derivative, which is negative 1 over 3 factorial times x cubed, plus 0 over 4 factorial times x to the 4th, plus 1 over 5 factorial times x to the 5th, plus 0 over 6 factorial times x to the 6th, plus negative 1 over 7 factorial times x to the 7th. So now let's clean this up. Okay, so of course that's gone. This ends up being just going to be x. That's that right there. This is gone. 0 divided by anything times anything is 0. Next up is going to be negative 1 x cubed. So it's negative x cubed over 3 factorial. This one's gone. It's a 0. Plus x to the 5th over 5 factorial. That's gone. It's a 0. And then minus x to the 7th over 7 factorial. And what we just did is we basically found this is going to be equal to the P7, the polynomial approximation of sine of x to the 7th degree. So now we're going to use this to figure out what is sine of 0.1. Oh my gosh, I'm so sorry. It is very loud over here. I'm really hoping you're not hearing all of it. They're talking to someone in Lebanon, and it's very, very loud. Okay, where was I? So if you use this function to figure out 0.1, what that means is you're going to be plugging in to the calculator 0.1 minus 0.1 cubed over 3 factorial plus 0.1 to the 5th over 5 factorial minus 0.1 to the 7th over 7 factorial. And you should get approximately 0.998. Now to find the error for your approximation, you do sine of 0.1 directly into the calculator, and it actually gives you 0.998. So what do you notice here? What is the error from our approximation to our actual function? It's almost 0. So the error is approximately 0%. And that's why we use Taylor polynomials. Okay? So, example 4. List the first 4 non-zero terms for the nth term for the Maclaurin series of sine of x. So we actually already have the P7th. So I don't need to really do, I don't really need to do the work again, right? So here it says the first 4 non-zero terms. Now this right here said find n equals 7, so we had to find the 0, 1, 2, 3, 4, 5, 6, 7 degrees. But for this question, it says list the first 4 non-zero terms. For that one, we have to actually just list the number of terms. So sine of x is approximated. We just did that here. So the first non-zero terms is going to be this guy right here. This one's non-zero. This one's non-zero. This one's non-zero, and this one's non-zero. So we already kind of did it in this problem. So the first non-zero terms are x minus x cubed over 3 prime plus x to the 5th over 5 prime minus x to the 7th over 7 prime. So, and this was given to us when n equals 0. This one was the first 4 non-zero terms. So n is 0 here. For this one, n was 1, right? You remember? Yep, n was 1. This one came from n equals 3, and this one came from n equals 5. Oh, no. That was 1. This one was from 3. This one was from 5. Sorry. And this one came from 7. Okay. So next up, we want to find the nth term for this Maclaurin series. So if this kept on going on forever and ever and ever, what would be our nth term? So we have to look for a pattern here. And you notice that the pattern is, first of all, one's positive, one's negative, one's positive, one's negative. So we just learned that that basically means this is alternating. Positive, negative, positive, negative. So we have to put down this term right here, -1 to the n. This will show us positive, negative. Next up, we notice that x is going up, odd numbers. The degree is odd numbers. So 1, 3, 5, 7. So basically from that, we know Sorry, I lied with these n's because we're going to need these n's. So here, the nth terms are going to be 0, 1, 2, 3. We're going to determine them like this to figure out our nth term, because these are the first 4 non-zero terms, and we're going to call them, this is our first term, our second term, our third term, our fourth term. So because of that, we can determine that this is going to be 2n plus 1. So if I plugged in 0, I should get the first degree. If I plugged in 1, I should get 2 times 1, which is 2, plus 1, I should get the third degree. If I plugged in 2, I should get the fifth degree. So that's what these are. These are going to help us determine what our nth term is. So it really has nothing to do with this n equals 7. All right, so that's the top part. We've kind of determined the nth term for the top part, divided by the same thing is happening on the bottom part. It's going from, technically this is 1 factorial, 3 factorial, 5 factorial. So it's very similar to the exponent. So there is our factorial equation. And then once we figure this out, we know that this is going to be a series starting at n equals 0 to infinity of -1 to the n, 2n plus 1, sorry, x to the 2n plus 1, all of that over 2n plus 1 factorial. Okay. I'm going to let you guys figure this one out. I can show you my work for it, but you should possibly put a pause, and you're going to find the Maclaurin series. So we know that x, which is c, is going to equal 0, of degree n equals 7 for f of x equals cosine of x. And then use it to find the first 4 non-zero terms, and then use it to find the nth term of the Maclaurin series. So I'm going to put down my key for a second so you can see the work. So again, step 1, I found the first 7 derivatives with the original function. I wrote out the approximation, because that is an approximation, for the whole thing. I canceled out any 0 terms, and I ended up with n equals 0, n equals 1, n equals 2, n equals 3. So these are the first 4 non-zero terms. And then from that, I found my nth term. Okay. Again, knowing that it's alternating between positive and negative, I have to have the alternating series term. Going from a degree of 0 here, which is different than sine of x, to a degree of 2, will give me this nth term. So 2 times 0 is 0. That will give me the first term. 2 times 1, right, because that's the first term, is going to give us 2, and so on. All right, and the same thing for example 6, you're going to find the Maclaurin series. So again, x equals c, which equals 0, of degree n equals 4. So for this one, you just got to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and f to the 4th prime of 0 of e to the x. Okay? And you know that the derivative of e to the x is just e to the x, so this is e to the 0. The derivative of this is just e to the 0. Derivative of this is just e to the x, so it's e to the 0, e to the 0. So it turns out that every term is 1. So when you plug it in to p4 of x for e to the x, the approximation, the first term is 1 plus 1. Technically it's over 1 factorial, but we don't really write it, so just keep that in mind. It kind of helps with remembering the formula. Times x to the 1, right? Plus 1 over 2 factorial times x squared, that's for the second derivative, plus 1 over 3 factorial, that's for the third derivative, times x cubed, plus for the fourth derivative, 1 over 4 factorial x to the 4th. So once you clean this up, it's just going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And then to figure out our nth term, this one's easy. It's just going to be remembering that when we start with our terms, this is 0, this is 1, this is 2, this is 3, this is 4. They are just increasing by 1 degree, so this is 0 degree, 1 degree, 2 degree. So the degree is x to the n, okay, right? X to the 0 gives us this. And the bottom is just going to be n factorial. When it's 0, it's 0 factorial. When it's 1, on the bottom here is 1 factorial. When it's 2, it's 2 factorial. So here is our nth term. All right, now we get into the Taylor polynomials. I'm going to stop this video just because it's going to take a while to upload, and I'm going to make a part 2 for examples 7 through 9.